Today, we want to get into one of the mechanical aspects of integration. Our thinking is that integration is multiplication, but one of the factors is continuously variable. We deal with the variable factors in a multiplication by dropping back to addition, because multiplication is just addition when everything is the same. We deal with the continuously variable part, by dropping back to a discrete set. We evaluate the function at a bunch of points and make rectangles. And then we do the calculus thing and think, what would happen if we had an infinite number of rectangles that were infinitely thin, but not zero thin? So our thinking is we start with our discrete sum. We apply calculus, taking a number of rectangles to infinity. That gets our continuous sum in the definite integral. Then the fundamental theorem of calculus comes along and says, here's how you calculate these infinite sums. Really what we're doing is we're taking this expression, f of x dx, and we're thinking of evaluating it for all these values, all those x values from a to b. Clearly, weird stuff has to be going on because this is a continuum, this interval from a to b. There's nowhere to put the pluses. That's why we need the fundamental theorem of calculus come along and say, hey, all you need to do is find an antiderivative. And so we're like, oh, awesome. All we need to do is find an antiderivative. It's one simple trick to evaluate your continuous sums. But then we get into the big problem, finding antiderivatives. And so that's what we want to talk about today. It feels a little bit early to do this, but it's a Monday and it's Mechanics Mondays. So we got to find some antiderivatives. This part over here where f prime of x is equal to f of x, I wrote it that way so I could fit it all on one line. But here's where I was saying that capital F is an antiderivative of little f. Let's get into finding antiderivatives. Here's the good news. Most of the antiderivatives that you're going to run across, especially here at the early stages, you already know them. We just need to take all of our derivative knowledge and send it back the other direction. So the first thing about finding antiderivatives is all the derivatives, finding antiderivatives, all the derivatives that you know, let's just turn those into antiderivatives. The notation that we're going to use is the indefinite integral. We're going to be using indefinite integral notation for antiderivatives. The way we're going to start this is we're going to take every derivative that we know and turn it into an antiderivative by flipping the notation around. So we'll start with something simple. We know that the derivative of x squared is 2x. We're going to take this derivative information and turn it into antiderivative information. This tells us that the antiderivative of 2x dx is x squared. or I should say, an antiderivative of 2x is x squared. An antiderivative of 2x is x squared. Why did I say an antiderivative and not the antiderivative? Because if there's a constant term, when we took the derivative, that went away. So the derivative of, say, x squared plus 1 is also 2x. X squared and x squared plus 1 have the same derivative. So we could say that an antiderivative of 2x dx is x squared plus 1. So there's another antiderivative of 2x. The only difference that we are going to get in all these antiderivatives is the constant at the end. The only difference between all these antiderivatives is the constant at the end, because the constant goes away when we take derivatives. So we don't know what constant was there. We can't make an inverse of the differentiation operation because we don't really know where we started without additional information. So what we're going to say and I heard most of you thinking this before, is we're just going to put a plus c. When we're finding antiderivatives, we're going to write the general antiderivative. We're going to say it's x squared plus c. This is going to be the general antiderivative of 2x. Because the derivative of x squared plus some constant will be 2x for whatever constant. C will be referred to as the constant of integration. C is the constant of integration. What we're doing when we find an antiderivative is defining a class of functions or a family of functions. If we have an additional piece of information about a member of that family that we want, then we can figure out what the plus c is. So the indefinite integral is a family of functions where the only difference is plus c. The antiderivative is a family of functions. If we have additional information about a particular member of the family, then we can find the plus C. We need additional information about a particular antiderivative to find a value of C. How's everybody? Okay. We're going to do an example. And this is a lot of overlap from the stuff we finished with last semester, or that you might have finished with last semester. So when everything makes sense in math class, you're like, oh, we've already done this. You should be like happy about that. Sometimes students are like, oh, we need to move on to more fancy things. It's like, oh, no, it's week 2. Be happy that this is stuff that you already know. When you're in a math class and everything makes sense, then just kind of like, all right, that's cool, right? Think about physics problems. When you start off in physics, you start off no friction, no air resistance, because that just makes things more complicated. So when you're doing physics and everything makes sense, you're like, oh, yes, this is much more comfortable. Besides, for the most part, if we're like throwing objects, if you're just like physically throwing an object, you're not throwing it hard enough for air resistance to be a factor anyway. I don't know. Does anybody here have a decent curveball? If you don't, then you're not throwing hard enough for air resistance to really make it better. I'm just kidding. It makes a difference all the way down to knuckleball. But if you just throw things not very hard, air resistance doesn't really matter. Like if I pick up one of these pens and drop it, it's not going to reach terminal velocity. It's only going like 4 feet. You know what I mean? And it's also not going to change if I drop it sideways or if I drop it straight down, or I put like an aerodynamic nose cone on it. It's not going fast enough for it to matter. So let's do an example. So here I've offered a description of a function. Find a function capital F of x such that capital F prime is sine x and capital F evaluated at 0 be 3. So I've given you 2 pieces of information because I want you to find 2 things. Number 1, I've given you a derivative. From this, we'll find an antiderivative, a family of functions. So this is where we go for the antiderivative. Oh, the general antiderivative. That's going to identify an entire family of functions. And then this additional piece of information where capital F at 0 is equal to 3, that will be a piece of information that allows us to find a particular member of that family. So that is information that we can use to find a particular member of the family. What function has a derivative of sine x? Negative cosine of x. We know that the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. So we use our antiderivative techniques to find the family of functions. F of x must have the form minus cosine of x plus some constants. Derivative of cosine is negative sine. The negatives cancel out, so we sine. The derivative of the constant is 0. There's our antiderivative, our general antiderivative, defining a family of functions. Now I'm going to use that f of 0 is equal to 3 to figure out what the plus c is equal to. So I'll just plug 0 into my general antiderivative. That'll give me an equation that I can solve for c. Cosine of 0 is 1. So 3 is negative 1 plus c. So c must be equal to 4. Now I just put these together, and the function that we were looking for is negative cosine x plus 4. Any questions? How's everybody okay? Everybody looks stunned. Oh, whoa. Antiderivatives? Yeah, we got to do Calc 1. All that derivative stuff, we have to do that backwards now. That's what happens in math class. You have to learn everything backwards and forward. The first stage of this process is going to be taking all those base derivatives that you know, and all those derivatives that you know before you had to do things like product rule, quotient rule, chain rule, and learn those backwards now. Write them with antiderivative notation, with the indefinite integral notation, and remember them. Then we're going to do an anti-chain rule and an anti-product rule. We don't need the quotient rule, so we don't need to do an anti-quotient rule. I think the quotient rule is fully aware that it's just a hanger-on in this whole process. Product rule and chain rule, we need those two. Quotient rule is just kind of extra. If you rewrite your quotient as a product and use the chain rule and the product rule, you get the quotient rule. So the quotient rule at least acts like it's fully aware that it's unnecessary, right? So it like steps in the background when it needs to. In the Justice League of Derivatives, the quotient rule realized that it's like the not Superman on the team. Because I think the whole Justice League is aware. It's like, well, we got Superman, so what are we all here for? And Superman being a good guy is like, oh, hey, we can't have a Justice League without like extra people, right? We can't be super friends all on our own. And so all the super friends are like, oh yeah, we're all super friends. And then Superman realizes like, oh, I don't really need these people, but I'm glad they feel good about themselves. You know what I mean? Like Batman. Batman is just some dude. He's kind of smart. Like, well, Batman should just be like staying at the Hall of Justice and directing things from afar. You know what I mean? It's like modern Justice League. It's like, oh, Superman should just have a cell phone. And Batman be like, oh, hey, there's a problem over here. And Superman's like, oh, got it. And after Superman hangs up, he's like, oh, I totally heard that. I have super hearing. And I'm almost there because I'm super fast. And I can fly into orbit to go even faster. So thanks, Batman. But he likes to make Batman feel like he's useful, even though Batman is just like some guy. You know what I mean? First step, very efficient. We're just going to double all the stuff that we know. All derivatives are now antiderivatives too. Let's start with what's going to be our favorites, which was our favorite from the derivatives. So recall that our favorite rule for derivatives is the powers of x, to the point where it's like, oh, if we can write stuff as powers of x, we totally want to do that because we like this one so much. Look at what the steps are. The steps are multiply by the exponent, subtract 1 from the exponent. So it's like distinct steps that we follow to find this this derivative. Multiply by exponents. And then subtract 1 from exponents. What we're trying to do is build an inverse, and an inverse means do the inverse operations in reverse order. That's how we invert a process. If we can look at the process as a sequence of steps, if we just do the inverse of each of those operations in reverse order, that will get us back to the beginning. So we're going to do inverse operations in reverse order. So since the last thing that happens in the derivative rule is to subtract 1 from the exponent, we're going to start by adding 1 to the exponent. And then we're going to invert to multiply by the exponent to divide by exponent. Thinking about the process will allow us to do an infinite number of problems all at once. So we can integrate the integral, or the integral of a power of x dx. We'll add 1 to the exponent and then divide by the exponents. Then we're going to make sure we put on the plus c because the derivative of every constant is equal to 0. That part went away. The reason I didn't just write this down because everybody would have believed me in the first place, because I wanted to bring up this inverse operations in reverse order thing, because that's us solving equations. I'm not sure we think about that enough. Now, this won't always work, because notice that this new expression had divide by the new exponent. There's division in our process. And that means there could be problems. I've got this 1 over n plus 1. I can't always have a 1 over n plus 1. This is not going to be okay if n is equal to -1, because then I have to divide by 0. And we know that we can't do that. Division by 0 is undefined. So this is only good for n, for when it's not, when n is not -1. This is still pretty good. It works for every other real value of n. So we just did an uncountable infinity of problems. That's pretty good return. That's very fast. But that's okay, because we have another derivative. What function has a derivative of 1 over x? Natural log of x. So the derivative of natural log of x is 1 over x. Here's our n equals -1 case. So if we turn this around into an antiderivative, the integral of 1 over x to x is natural log of x is natural log of x plus c. There's more stuff that we need here, though. Going in this direction, I need to put the x in absolute values. 1 over x and natural log of x both agree, can't have a 0 there. But 1 over x is okay with negative numbers. Natural log of x not okay with negative numbers. We didn't need to worry about that with the derivatives, because we're starting with natural log of x. And so we're already restricted. So we're just the positives. Derivative is 1 over x. It's like, all right, I'll just accept your no negatives. But going the other direction, when we start with 1 over x, we got positives and negatives, just like not 0. So when we find the antiderivative, we got natural log of absolute value of x. If you forget the absolute value of x, when you integrate 1 over x, I take off 1,000,000 points. It's very dangerous. Losing 1,000,000 points at this point in your mathematical career kind of puts you back all the way to 4th grade. I've done the calculations. Depends on the school district. So you might end up in 4th grade math all over again. And it's like this is like hardcore MMO style. You just lose XP and you have to get that XP back. It's not just like weak MMO where you just have to like run back to your corpse as a ghost. You know what I'm talking about? And all you have to do is pay gold to get your equipment fixed. I don't know what the MMO escape is like anymore. The last one I played was World of Warcraft. And that was a long time. Any questions? Does World of Warcraft still exist? People still play it? Like a lot of people, or just like, wow. So at one point it was like up to like 10 million. It was like over 10 million people playing. And that's kind of at the point where I failed. I quit World of Warcraft the same way I quit smoking. It took like 4 tries. It was crazy. I'm playing World of Warcraft. It's like, ah, no, this is crazy. I'm not doing this anymore. Say goodbye to my guild. Off I went. Burning Crusade came out. I don't know how many of you play World of Warcraft. None of you are old enough to have played World of Warcraft at the time that Burning Crusade came out. But everyone's like, oh, this is good. You should come back. I'm like, oh, nah, F that. I'm not coming back. Then like the tail end of Burning Crusade, like right before Wrath of the Lich King was announced, like right when they were thinking, oh, what's it going to be? Lich King came after that, right? Yeah, I'm pretty sure. I can't remember very well anymore. And anyway, pop in at the tail end of Burning Crusade, and I was like, oh, this is kind of cool. Something. You know what I mean? And then I hung out for Wrath of the Lich King, because sucked back in. You know what I mean? It's the same way that you first quit smoking. When you first quit smoking, if you do it when you're young enough, like before you have like lung cancer, you're like, well, I'm not gonna smoke anymore. And it's like, oh, cool. And then you go out with your friends, you're hanging out at a bar, then all of a sudden someone's like, oh, Leach, I thought you quit smoking. I'm like, oh, I did. Son of a. And there's like a cigarette in my hand. Oh, I guess I forgot that I did that. So I was like sucked back in, so I had to quit again. Anyway. 2.4, that's still a lot. All right, so your job right now is to work on chapter 5. Chapter 5 is old stuff. The emphasis on the chapter 5 homework is on thinking about integration. Finding antiderivatives is us moving on to chapter 6. We're going to learn how to find some antiderivatives and what we can do with antiderivatives. By the end of the week, we're not going to have finished chapter 5. We're not going to have finished chapter 6, but we will be talking about ideas from chapter 7, because we've got to invert our product rule and invert our chain rule. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.